Okay, welcome back. So I'm going to continue discussing this. So with the private ownership of land, as I said before, so this is a typical dynamic problem, dynamic programming problem. And you know how to attack such problems, right? So there is a first order condition with respect to the choice variable, control variable, and there's then the envelope condition, right? So when we write these things, very similarly, as you know, we take the derivative of the Bellman equation, the right-hand side, with respect to n, and then we write the envelope condition by taking the derivative with respect to xt, right? Xt is our state variable. So then, once again, we are interested in steady states, okay? Now, with the private ownership of land and taking into account, now you realize one thing, right? The main difference. This part is the difference with the earlier approach, right? So in the hunter-gatherer society, this term was not there, right? Now, when I take into account, of course, the fertility level creates a disutility, right? This term is negative. Why? Because there is value associated with land. So if I leave more land tomorrow, what I expect is to have a higher marginal utility of land. But then if I increase my fertility, of course, this entire term decreases. So this introduces the trade-off, a dynamic trade-off to the problem. Okay, so the main difference is there. But again, we are interested in the steady state. So it's the steady state, once again, will have constant population. All right, so population growth rate will be equal to just 0. So with each person have 1 kid. So there is a steady state described by these equations. Income will be fixed, consumption will be fixed, value will be fixed, and the derivative, the marginal value of land will also be fixed. Okay. This, of course, requires the value function to be unique and etc. But this problem is very simple. There's all the nice continuity and concavity assumptions involved. In fact, the period utility function that you see here is strictly concave. So then there's no particular problem with looking for a unique value function and the unique, therefore, derivative. So once we put these into these equations, so once you rewrite these equations that describe the optimal path for the steady state, you have 2 equations, right? And basically, you start with the envelope condition. Envelope condition solves v prime as a function of x. Okay. Then you replace this in the first order condition for fertility, right? Then you find first the steady state level of x. All right, so this is x to the alpha, but you can write x using that. And the main difference here will be that term, a times alpha times beta. All right, so this part was not there before. Using this, of course, you can write income level and again consumption level. And once again, this alpha beta term was not there before because that's important. So what is beta? Beta is the discount factor, right? And what was alpha? Alpha is the marginal product. So the parameter of the production function that determines the severity of diminishing returns, right? So when you take your decision in terms of fertility, Why does this parameter affect your choices? Because it affects the marginal productivity of land, right? Remember, X is land per capita. So you find Y, you find C. Then we can compare the two equilibria, right? We can now compare what's the role of private ownership. Okay, now in the hunter-gatherer society, we had this consumption level, right? In the private ownership economy, we have this. And here, we make a particular assumption to make this entire story consistent by assuming that. Why do we assume that? Well, technically, this must be positive, right? This is consumption. So beta is already less than 1. So this part is positive, but this part should also be positive, and there is no guarantee. There's no way other than assuming this to ensure that consumption is positive. Okay, but this also tells you that so this basically originates, by the way, from our choice of an interior equilibrium for fertility, right? So we assume that these people will have kids. All right. So we kind of, we have to assume that eta is sufficiently large. All right. So consumption is larger. How do I see that? Well, numerator is bigger, denominator is smaller. Right. So it is then the case. How do I know that? Land per capita will be larger. So, by the way, land per capita larger means population to be smaller, right? So there is a steady state population level, and in the steady state, of course, land is fixed, so this will be lower. Okay, because as you remember, x is L over N. L is fixed, so if x is larger, then population level, that's important, population level at the steady state of the private ownership economy is smaller. And that's also meaningful. Why? Because we are now sustaining a lower level of population, because always at each period we transfer resources to future. Okay, we optimally choose that. So once again, you can see the difference here. So if you write this, you have 1 minus beta plus eta k eta a, right? 1 over alpha, but here you have something else, right? So again, this term changes everything. So, okay, there is one difference. What else? Well, we have some remarks. Okay, so in the private ownership economy that we studied, we looked at an egalitarian equilibrium. All right, so people are alike, even if they have land, they have equal amount of land, they have the same preferences. So this, of course, is not true in reality, and in a moment we're going to see a two-class society, which is much more realistic. So the simple reason behind the fact that private ownership economy obtains higher consumption is that there's optimal management of land. Okay, that's the key. So if you think about more in a more sophisticated manner in terms of resource allocation in a dynamic sense, then you get a nicer result under private ownership, because with communal ownership, under purely egalitarian, no private ownership economy, people don't really care about how much land they have and how much land they leave to their kids. But with private ownership, of course, they care about that. This is not entirely satisfactory model, perhaps, for hunting gathering. There could be more sophisticated models, and there are actually in the literature more sophisticated models. For instance, there are models where two different hunter-gatherer societies are in conflict with each other over natural resources. All right. So obviously, then there is this additional constraint that you want to have a larger population for military reasons, right? So yes, you want to manage your land optimally. You want to have fewer kids to make your kids better in the future. But if there is a possibility of war, there's a possibility of conflict with a rival community of hunter-gatherers, then you also need to have a larger population for military reasons. Then there are more complicated stories, of course, behind that, and choosing fertility is not that similar. So it's not basically the so this story could be extended, right? There is also the possibility that, so in a given site, in a given natural site, resources can be modeled differently, right? Resources could be modeled in this particular way. Okay, so initially it is constant, right? Initially it is constant. Then how much you eat at each period determines how much you leave for future. Okay, so then your so you may label this total exploitation. Okay, so fruits and vegetables are given, so you eat them. Of course, naturally, there could be also a growth factor as well, right? So there could be also a growth factor that depends on LT, right? So it's better actually if we denote it by G. All right. So the story could be extended. All right. Again, rival communities. So there's community I and community J. So usually these conflict resolution models assume that probability of group I to win a conflict is proportional to the size of the group. Okay, the relative size of the group could be important for winning the conflict. All right, so then population share is important, and so on and so forth. So there could be other models of hunting gathering, but this is the simplest that we see the economic logic behind optimal land accumulation. Okay. Now, in the rest of the class, we're going to look at a much more realistic society, okay? A society of unequal distribution of land. In fact, one social class will be landless workers, so they will have no land. They're just workers. They have only the labor supply they have for sustaining their lives. And there's also this class of landowners. So okay, so they will own the entire land in the economy, and their populations now will be differentiated. So in the notation, we have an L for the number of landowners in a particular generation and W as the number of workers in a particular generation. Okay. Now, we also differentiate two things: land per worker versus land per landowner, right? So X is the similar thing that we studied before, right? So it is land per landowner. But now land per worker is different, right? Because farms, if you think about it, farms are owned by these landowners, but each farm will be employing a given number of workers. Okay. So production, of course, will be depending on land per worker, but incomes and how the landowner takes the optimal decision towards fertility depends on land per landowner, obviously. Okay. For the workers, the situation is exactly the same as in the hunter-gatherer society, right? Since they do not have land, and they can, so in this society, of course, we assume that they also do not accumulate resources. So there's no money involved, all right? So this is just a feudal economy. So if you are born landless, you remain landless, and your kids will also be landless. Okay, so this is like a caste system. And if you are a landowner, then you're gonna behave exactly as in the case of private ownership economy. All right. So basically, we are merging the two economies that we studied today for a more realistic understanding of actual historical economies. Okay. Production technology is the same as well. So I write this now as A times Z to the alpha. Z is again land per worker, right? Right now I'm not writing it. I'm not writing X here. It's Z. Land per worker matters for production. Okay. So how can the landowners obtain income? Of course, that's through the land market. All right. So you may assume that landowners are not really the farmers themselves. So landowners basically obtain rent income by giving their lands for the farmers. Okay, so farmers could be just firms. So there could be the possibility that many different people are owning such firms, and all of these people would also be perhaps landowners or workers. It doesn't really matter, because there's constant returns to scale. So all income will either be wage or rent. Okay, so the entire output will be eventually transformed into either workers' wage or the landowner's rent. Okay, but in a competitive equilibrium, so if you think about it, so if this is the production, right? So if this is the production, the profit could be written in this way, and out of this, of course, you find the demand function for land. Okay. Now the rest of the output goes to workers. Okay. Because there will be constant profits, right? So of course this is so there is also wage So if you think about it, so this is your this is actually your problem. R, sorry, W and W minus R L, right? So you divide all of this with NW, right? So you have already Z here, so this is divided by NW, so this becomes A times Z alpha. Okay, so there is W here. So then you find W as the remaining fraction of output given to the workers. Okay. Clearly, we have this level of income for the worker, right? Remember the hunter-gatherer model. In a steady state, they behave, since workers behave exactly as in this case, so we have this, but then we know that this must be equal to that, right? So if there is a steady state level of length per worker, then this length per worker found in this way, right? In the steady state, this must be satisfied because they behave as if they are hunter-gatherers. If you equate this to the wage in the steady state, you find Z, length per worker. After finding length per worker, you can find the total number of workers in the steady state, all right? So the situation is like this. First, you solve the hunter-gatherer problem for workers. You find income, then you find Z, then you find NW. Okay, so that's for the workers. Now for the landowners, you're gonna have the dynamic programming problem. Okay, but before that, actually, so what is this? So okay, that's the same thing. Of course, if you know Z, land per worker in the steady state, you also know rent, right? The steady state level of rent is also here. For the landowners, of course, their fertility behavior will be different, and you're going to solve this through X variable. Remember, X is, that's important. X is now land per landowner. Okay. So if you do that, the same principles, right? You again find the steady state, exactly the same logic, okay? And once you do this, you find the steady state value of land per landowner, okay? This one. This right here is the steady state. How do you calculate it? Well, you first find the value, then after knowing the value, you put this back on here, and you find X as a function of R, but you know what R is. R is alpha times A, Z to the alpha minus 1. Okay? And you know what Z is as well. So knowing that, you also have this. Okay? You also have this, and now you can compare class divisions. Okay, You can look at consumption levels, okay, consumption of a worker family and consumption of a landowner family, okay? And directly you see landowner consumption. And of course, here we also make a particular parametric assumption that says eta is greater than beta. Okay, once again, for this consumption level to be positive and economically meaningful. All right, so that's the only parametric assumption we are making actually. So what else you can do? Well, let me summarize that to you, and this is actually an exercise, a set of exercises that you can. So you can first explicitly solve for class sizes, okay? How many workers will be around and how many landowners will be around. Interestingly, these are endogenous, right? So even though there is a given social structure, okay, so landless people remain landless, landowners' kids become landowners themselves, right? So this is like the caste system, but a Malthusian steady state requires class sizes to be endogenous, all right? Because population will adjust to resources. That's the key. Population will adjust to the resources in the long run, all right? Then you can calculate welfare levels, okay? So by making such solutions, by the way, you will learn certain things about the class structure, certain things about how can landowner wealth differ from workers' wealth, okay? Then you can also find a parametric condition that implies CL greater than CW. That's obvious, I just showed you. More interestingly, you can use this model to study poor laws. Remember from economic history, especially for the case of England, there was this huge discussion about, taxing the rich and distributing the tax revenue to the poor, landless people. Okay, now you can actually study it, right? Because now you can put a marginal rent tax, tau, right? So tau will be a tax rate between 0 and 1. So it will tax the rent income at this marginal rate tau, then distribute the tax revenue as a form of transfer to workers, right? So the budget constraints will differ. And the government budget constraint will satisfy this. That's a nice exercise. You introduce one new parameter, tau, one new variable b, and one new equation to extend the model to study the effects of such a tax transfer scheme. And you can actually calculate everything, right? So you can actually look at different steady states, and for different levels of tau, suppose that you have different levels of tau. 0, this is the same model we have, right? Because if tau is 0, be careful, if tau is 0, BT is 0, WT and rent income will be the same. But then you will have, let's say, different levels of this tax parameter, okay? And for each tax level, you can show me the relative class size in the steady state. you can show me consumption differences, you can show me wealth differences, and so on and so forth. Okay, so how does that type of poor law would change the fate of the Malthusian societies? So that's an interesting exercise. Now let me stop here, because that's all I'm going to cover for today. And now if you have questions, I can answer them. If you have comments, we can discuss. Otherwise, take these exercises as not for credit. And I will upload your next assignment today or tomorrow about the poverty traps. It will be an essay assignment. Now, if you have questions, I can answer them.
Professor, as I remember, Malthusian theory says that food production increases arithmetically, and population increases rapidly than the food production, and these developments leads to famines or wars. So can we extend the model, adding a shock like that, a war or famines? Is it possible?
Yes, it is possible. Actually, I can recommend one paper, which is, so I can actually recommend two papers. One is mine, and I'm gonna present that paper in 1.5 hours in the department seminar at 9 Eylül University. So that paper is in my website. It is called Technology and Survival in Pre-Industrial England, a Malthusian View. This paper is now in the revision process for a journal. So the first round revision I am just trying to complete. The other paper is again published in Journal of Population Economics, and it's by Foreman and Pack. So they extend. So let me. Foreman Pack is one of the authors. The journal is Journal of Population Economics, either 2020 or 2021. And my paper is in my website, but I can also send you the codes and all the other stuff. So you can, of course, extend the model with the survival shocks, with famines, with all other catastrophic events. That only adds, of course, depending on your question, the model becomes more realistic and more complex. What we are doing here is looking at these simple mechanisms. But you can extend the models. Foreman Pack's paper is a nice one, so you can actually read. Actually, let me send this, upload this paper to the system so you can read it. Let me if you cannot find it, find it in the HUSAM system so you can read it. It's a nice paper. And wars and all this stuff. So there's also one nice paper by Niels Lagerlöf. It's about a Malthus to solo economy. So basically, it shows that it's a paper about war. So you can find it in the website of this economist. So it argues that because economies become increasingly less Malthusian, right? So they, thanks to the technology, they beat the pressure of natural resources. Eventually, the likelihood of wars decrease. Okay, because these empires in the pre-industrial period were all after land. Land was the main source of prosperity. Okay, for this reason they entered into war. Okay, all of these empires were after these natural resources. But now, in the age of technology, of course, with an exception of crude oil, right? What you don't and what you really care about is not really land. What you care is knowledge, or technology, or science, or other stuff. But yes, you can extend such models in many different dimensions, actually.
Thank you.
Any other question or comment? Okay, then. So, as I said before, I'm going to upload some stuff, including your assignment. It will be an essay assignment about the Millennium Development Goals and poverty problems in the world. So you will write a short essay, and by the way, I'm uploading the class meetings to YouTube. You know that, right? So, and I'm sharing the links in the university system, so you can always see the class meeting videos there. Okay, so next week we're going to continue with what? Let me check. We're going to continue with something. Yes, next week we're going to look at unified growth theory, finally. Unified growth theory is the theory that unifies, obviously, the two equilibria, the growth equilibrium and the stagnation equilibrium, right? Because historically, we see that economies were actually poor, and they were within, for thousands of years, they were within a Malthusian equilibrium. But then they transited into what we call modern growth. Okay, so unified growth theory will show you how you can model this as a continuous and endogenous process. So see you next week then.
Thank you.
Bye-bye.
All right, bye-bye.